for the unit Solutions, Dilute Solutions and Colligative Properties, in our previous lecture we discussed thermodynamic calculation of molar depression constant, measurement of freezing point depression, some examples related to freezing point depression and osmosis. For the knowledge of osmosis, it is required that we discuss osmotic pressure. Hence, in today's lecture, we are going to discuss osmotic pressure, reverse osmosis, theory of osmosis, measurement of osmotic pressure, applications of osmotic pressure and some examples related to osmotic pressure. Before explaining the osmotic pressure, let us differentiate between osmosis and diffusion. In case of diffusion, solute and solvent particles both move in opposite directions, but in case of osmosis, only solvent particles move. There is another difference between osmosis and diffusion. In case of osmosis, a semi-permeable membrane is required, but in case of diffusion, no semi-permeable membrane is required. Now we are going to discuss osmotic pressure. The hydrostatic pressure which is developed on the solution because of osmosis is called osmotic pressure. It can also be said that the hydrostatic pressure built up on the solution which stops osmosis is called osmotic pressure. So, osmotic pressure is a hydrostatic pressure. In this figure, we have taken an inverted Thistell funnel covered with a semi-permeable membrane and filled with a glucose solution. This Thistell funnel is placed in water. In second figure, you can see water rises due to osmosis, and H denotes the height attained after osmotic equilibrium has been reached. At this situation, osmotic pressure is given as pi is equal to H dG. Here pi denotes osmotic pressure, H is the increase in level due to osmosis, D is density of solution and G denotes acceleration due to gravity. Actually, this method does not give accurate osmotic pressure. It is because dilution has been taken place because of osmosis and concentration of the solution continuously changes because of osmosis. Osmotic pressure can also be defined in another way. If we take an apparatus consists of two chambers separated by a semi-permeable membrane. One side it contains solution and other side it is filled with water, or it can be said that pure solvent. Now, because of osmosis, solvent will start moving towards solution through semi-permeable membrane. To stop this osmosis, an external pressure can be applied, and at the situation when the osmosis stops, because of this external pressure, osmotic equilibrium has been attained. Hence, the external pressure which is applied to the solution side to stop osmosis is defined as osmotic pressure. The same effect can also be produced by applying negative pressure towards the pure solvent side. Osmotic pressure is presented as pi is equal to CRT. As you know, pi is osmotic pressure, C is concentration of the solution which can also be denoted by molarity. R is gas constant. Its value is 0.0821 in liter atmosphere per mole per Kelvin. T is temperature in Kelvin. R can also be replaced by S, where we can say S is a solution constant. Molecular masses of non-volatile substances can be determined with the help of osmotic pressure. For this purpose, a known weight of non-volatile solute is to be taken to make a known volume of the solution. Let us take W grams of the solute and prepare V liters of the solution. Then pi will be equal to NaRT upon V. Here Na is the number of moles of solute, R is gas constant. In case of solution, R can be replaced by S. T is temperature in Kelvin and V is the volume of the solution in liters. Na can be calculated as Wa upon Ma, where Wa is the weight of solute and Ma is the molecular mass of the solute. This method is exceptionally suitable to measure the molecular mass of macromolecules like proteins or polymers. It is because in case of these molecules, other colligative properties like elevation in boiling point or depression in freezing point are too small to be measured, but osmotic pressure is measurable. On the basis of osmotic pressure, solutions can be divided in three categories: isotonic solutions, hypotonic solutions and hypertonic solutions. Isotonic solutions are those solutions whose osmotic pressures are same. The solution whose osmotic pressure is lesser is called hypotonic solution. The concentration of hypotonic solution is also less. If we place a cell in hypotonic solution, the solvent will flow inside the cell and hemolysis will occur. Now we will discuss hypertonic solutions. The solution with higher osmotic pressure is called hypertonic solution. The concentration of hypertonic solution is greater. If we place a cell in hypertonic solution, the solvent particles will move outside the cell and crenation results. In this figure also, you can see if two solutions are separated by a semi-permeable membrane, one solution is hypotonic solution. Here the concentration of solvent is larger as compared to solute. The other solution is hypertonic solution. Here the concentration of solvent is lesser than the concentration of solute. In this case, solvent molecules will flow from hypotonic solution to hypertonic solution through semi-permeable membrane. If the red blood cell is placed in 5% sodium chloride solution, which is a hypertonic medium, the water will flow out of the cell and cell will shrink. Actually, 0.16 molar sodium chloride solution or 0.91% weight by weight sodium chloride solution is isotonic with red blood cells. In this figure, you can see in first case the cell is placed in hypertonic solution, because of which it shrinks. In second case, the cell is placed in hypotonic solution, because of which water flows inside the cell and it swells. But in the third case, cell is placed in isotonic solution and it neither shrinks nor swells. Here is an example for better understanding of osmotic pressure. A solution containing 8.6 grams per liter of urea was found to be isotonic with a 5% solution of an organic non-volatile solute at 298 Kelvin. Now, what is the molecular mass of the organic solute? You know that molecular mass of the urea is 60. As osmotic pressure is given by CRT, let us take osmotic pressure of urea equal to pi 1 and osmotic pressure of unknown compound equal to pi 2. As these two solutions are isotonic, hence pi 1 will be equal to pi 2. The weight of urea is taken as 8.6 grams per liter. The molecular mass of urea is 60. Hence, osmotic pressure of urea will be equal to 8.6 RT upon 60. In case of unknown compound, it is a 5% solution, which means 5 grams of solute is dissolved in 100 ml of solution, that is 0.1 liters of the solution. Therefore, the osmotic pressure of unknown solution will be equal to 5 RT upon 0.1 into its molecular mass. On equating, we will get the molecular mass of unknown solute, which is equal to 348.9 grams per mole. Let us discuss another example. What is the relationship between osmotic pressure of 10 grams of glucose, 10 grams of urea and 10 grams of sucrose, which are dissolved in 250 ml of water respectively at 273 Kelvin. P1 is the osmotic pressure of glucose, P2 is the osmotic pressure of urea and P3 is the osmotic pressure of sucrose. Let us first calculate the number of moles of glucose, urea and sucrose. Molecular mass of glucose is 180, hence number of moles of glucose are 10 upon 180 equal to 0.055. Molecular mass of urea is 60, hence number of moles of urea are equal to 10 upon 60, which is equal to 0.167. Molecular mass of sucrose is 342, hence its number of moles are 10 upon 342, which is equal to 0.029. As osmotic pressure is directly proportional to number of moles, therefore osmotic pressure will be in the order P2 greater than P1 greater than P3. It is because N2 is greater than N1, which is again greater than N3. Now we will discuss another useful phenomena related to osmosis, known as reverse osmosis. If a pressure greater than osmotic pressure is applied on the solution side, the solvent particles will move from solution side to the solvent side. That is, the direction of osmosis can be reversed if the pressure greater than osmotic pressure is applied on solution side. This phenomena is known as reverse osmosis. Reverse osmosis has large application in purification of water, especially in desalination of seawater. The apparatus used for this process can be seen in this figure. The functioning of semi-permeable membrane depends upon the nature of membrane used and the nature of solvent and solute used. Even then, there are many theories which explains the functioning of semi-permeable membrane. These theories are the molecular sieve theory, membrane solution theory, vapor pressure theory and membrane bombardment theory. Let us discuss the molecular sieve theory. According to this theory, semi-permeable membranes contains small pores which acts as sieves for the smaller particles, solvents, because sometimes if the solute particles are smaller than the solvent particles, even then the solvent particles pass through the membrane. That is, the membrane acts as a sieve for solvent particles only, even if the size of solute particles is smaller than the size of solvent particles. Now we are going to discuss second theory, which is known as membrane solution theory. Some protein membranes which contain functional groups like COOH, OH or NH2 form hydrogen bond with the water when water is used as solvent. This water forms a solution, or we can say membrane solution, with the material of membrane. The water flows through membrane solution from larger concentration of water towards lower concentration of water. That is, solvent particles move from low concentration of solute towards high concentration of solute. Next theory is vapor pressure theory. This theory suggests that semi-permeable membrane has many fine holes which acts as capillaries. These capillaries are not wetted by water or solution. Hence, water remains at one side of the capillary and solution remains at the other. Water vapor remains in between solvent and solution, or you can say water and solution. As the vapor pressure of pure solvent, that is water, is larger than the solution. Hence, this vapor diffuses from pure solvent side to solution sides. This theory is best to explain the functioning of semi-permeable membrane. Next theory is membrane bombardment theory. This theory suggests that osmosis results because of the bombardment pressure created by solvent particles on both the sides, that is pure solvent side and the solution side. As the number of solvent particles on pure solvent side are greater, hence the total bombardments per unit area on the pure solvent side are greater. But on the solution side, some surface area is occupied by solute particles, hence total bombardments per unit area is less. Therefore, water molecules or solvent molecules migrate from high concentration of solvent to lower concentration of solvent, or you can say low concentration of solute towards high concentration of solute. We can measure osmotic pressure experimentally by many methods. The first technique which we are going to discuss is Berkeley's and Hartley's apparatus. The apparatus consists of a strong steel vessel into which a porous pot is fitted. The walls of the porous pot are coated with copper ferrocyanide. The water level falls in the indicator tube. This can be stopped by applying pressure using the plunger. The pressure applied is equal to the osmotic pressure. This can be recorded by using a pressure gauge. This method has many advantages. The first one is that this method is quick and accurate. The concentration of solution does not change with time, hence this method gives the correct osmotic pressure. As the osmotic pressure is balanced by pressure gauge, hence there is no tension on the semi-permeable membrane. Therefore, there are no chances of breaking or bursting of semi-permeable membrane. The next method which we are going to discuss is Pfeffer's method. The apparatus used by Pfeffer for determination of osmotic pressure consists of a porous pot with copper ferrocyanide membrane deposited in its walls and having a glass top cemented to it. The glass top has an open tube and a closed mercury manometer in the side. The apparatus is filled with a solution under examination through the tube, which is then sealed off. The pot is now placed in pure water maintained at constant temperature. The water passes across the membrane into the solution and develops a pressure on the manometer. The highest pressure registered by the manometer gives the osmotic pressure of the solution. The Pfeffer's method suffers from two disadvantages. First one is that it takes too many days to give the highest pressure. And the second one is that it cannot be used for measuring high osmotic pressures because in this case there is a tension on semi-permeable membrane which can cause bursting of the membrane. Now we are going to discuss Fraser's method. Morse and Fraser used the same technique, but they deposited the copper ferrocyanide electrolytically. As the membrane was more stout, they were able to measure high osmotic pressures, that is up to 300 atmospheres. The porous cell impregnated with copper ferrocyanide is filled with water and immersed in a vessel containing the aqueous solution. The pressure is measured by means of an attached manometer. The system is allowed to stand until there is no further increase in pressure. Then the osmotic pressure is just balanced by the hydrostatic pressure in the column of the solution. Osmosis has many applications in day-to-day life. One of them is the limp carrot becomes firm when it is placed in water because water enters into the carrot due to the osmosis. Salty food causes retention of water and swelling of tissues. This condition is known as edema. Water moves into the plants because of osmosis. Salt added to meat or sugar to the fruits prevents bacterial infection because bacterium placed on this salt or sugar loses water and die. If cucumber is placed in sodium chloride solution, it loses water and shrivels up to become pickle. These were some applications of osmosis in day-to-day life. Now let us revise what we have discussed today. First, we discussed osmotic pressure. Then we discussed reverse osmosis, which can be used for the desalination of seawater. 4 theories for osmosis were discussed, which are used for the functioning of semi-permeable membrane. Different experimental techniques for the measurement of osmotic pressure were discussed. In last, we discussed some applications of osmotic pressure. In next lecture, we will deduce a relationship between relative lowering of vapor pressure and osmotic pressure, and we will also discuss Van 't Hoff theory for osmosis.